Welcome to The Explainer. Today, we're diving into a really cool scientific technique called supercritical fluid chromatography. It's a fascinating method it's totally changing the game for chemists trying to analyze some of the trickiest molecules you can imagine.
Okay, so to really get this, let's start with the basic problem. Imagine you're a chemist. You've got this complex goop, a mix of all sorts of different molecules, and your job is to figure out exactly what's in there. You need to sort them out perfectly. For a long time, you really only had two main tools in your toolbox.
On one hand, you had gas chromatography, or GC, great for smaller, tough molecules that you can heat up until they turn into a gas. On the other hand, you had high-performance liquid chromatography, HPLC, which is the absolute workhorse for anything that dissolves nicely in a liquid.
But this left a huge, frustrating gap. I mean, what are you supposed to do with the stuff that's too big or too delicate to be vaporized for GC, but also doesn't play well with the detectors you typically use in HPLC? For a long time, these were the intractable molecules, and they were a massive headache.
And this is where our hero enters the story: supercritical fluid chromatography, SFC for short. It's a hybrid technique, and it was designed specifically to bridge that gap. It basically takes the best parts of gas and liquid chromatography and smash them together to handle those really tricky compounds.
So what's the secret weapon? What gives SFC its power? Well, the answer lies in a really unique, kind of strange phase of matter, something that's not quite a gas and not quite a liquid either.
Now, you might think this is some brand new tech, but the idea itself has been kicking around for a while. It was first described way back in 1962. But, it took decades of innovation. From the first clunky commercial machines in the 80s to today's sleek, powerful systems, for SFC to really mature and become the powerhouse it is now.
Okay, so the key here is what's called the mobile phase. That's the stuff that carries your sample through the machine. SFC uses what's known as a supercritical fluid. And you get this when you take a substance, usually something like carbon dioxide, and you put it under pressure and heat it up past its own special critical point.
Think of it this way. We all learned about solid, liquid, and gas in school, right? But if you crank up both the temperature and the pressure past a certain threshold, the substance enters this totally different fourth state where the line between liquid and gas just disappears. It's both, and it's neither.
And it's the properties of this weird, in-between state that make it the absolute perfect Goldilocks medium for sorting molecules. It's not too much like a gas, not too much like a liquid, it's just right.
And this table just illustrates the magic perfectly. A supercritical fluid has a medium density, so it's dense enough to dissolve things just like a liquid can. But, and this is the kicker, it has a super low viscosity and it diffuses really easily, just like a gas. That means it can zip through a chromatography column with almost no resistance, carrying the sample along with incredible speed and efficiency.
All right, so that's the theory. How does this just right fluid actually stack up against the classic techniques when the rubber meets the road? Well, the difference is pretty dramatic. Because of that gas-like low viscosity we were just talking about, you can push the mobile phase in SFC through the system at much, much higher speeds. We're talking about 4 times faster than you could with HPLC, all while keeping that beautiful, clean separation between molecules. For any lab where time is a factor, that is a huge, huge win.
And hey, the proof is in the pudding. Just look at this example, separating the different forms of metoprolol, a beta blocker drug. With HPLC, it takes 22 minutes, and you get a decent result. With SFC, you get a much sharper, cleaner, higher resolution result in just 6 minutes. It's faster and it's better. It's not even a contest.
But listen, the benefits of SFC go way beyond just pure speed. This tech is a major leap forward in a few key areas, which is what makes it such a powerful tool for the modern world.
It really is a triple threat. We've seen it's faster, it's also way greener, because the most common fluid it uses is plain old carbon dioxide, non-toxic, cheap, and it drastically cuts down on the need for harsh, nasty solvents. And finally, it's stronger. It gives you higher resolution, and it can analyze those fragile molecules that would just fall apart under the heat of gas chromatography. And this green aspect is a really big deal. Labs all over the world are trying to be more sustainable, and SFC gives them a way to slash their chemical waste and lower their operating costs, all without sacrificing performance. It's a total win-win.
So, what does this all mean for science, for industry, and maybe more to the point, why should any of this matter to you?
Well, SFC is already having a massive impact on industries that touch our lives every single day. It's used to make sure the medicines we take are pure, to analyze what's in our food, to develop new plastics and materials, and to test for things like pesticides in the environment. It's especially crucial for what's called chiral separations. That's telling the difference between mirror image molecules, which can be life or death in drug development.
Just how big an impact are we talking about? Well, way back in the 80s, when this technology was still pretty new, one expert estimated that SFC could probably solve the problems for about 25%, a quarter, of all the chemical mixtures that were considered impossible to separate back then. And with today's instruments, you better believe that number is only going up.
So in the end, supercritical fluid chromatography is so much more than just a clever lab technique. It's a perfect example of how exploring the absolute fundamentals of matter, that weird, blurry line between a liquid and a gas, can lead to incredibly powerful tools that solve real-world problems. And it really makes you wonder, doesn't it? What other amazing innovations are just waiting for us, hiding in plain sight?